Hello friends, so welcome to the lecture on pseudo-inverse and singular value decomposition. In the last lecture we have learned least square approximation of overdetermined and underdetermined systems. However, we have used the matrix A transpose into A in case of overdetermined system and A into A transpose in case of underdetermined system, and in particular for finding the pseudo inverse we have used the inverse of these two matrices. At that point I told you that if the inverse does not exist, then we will discuss this case later. So, in this lecture we will discuss that case. So, let Ax equals to B be an overdetermined system where A is a m by n matrix with m greater than equals to n, because it is an overdetermined system. So, in the last lecture we have learned the least square approximation of this can be written as like this: x equals to A plus into B, where A plus is the pseudo inverse of A and it is defined as A transpose A inverse into A transpose. So, if rank of the matrix A is less than n, this implies that A transpose A and the determinant of A transpose A equals to 0, and hence A transpose A inverse does not exist. So, now question is how to find least square approximation of such a system. So, for doing this we will make use of singular value decomposition for calculating the pseudo inverse in this particular case. So, let A equals to U S V transpose be the singular value decomposition of matrix A. Where U is a m by m orthogonal matrix and V is a n by n orthogonal matrix. And the matrix S is a m by n matrix containing the singular values of A. So, means we are using here full singular value decomposition. So, now we are having a system Ax equals to B. So, A can be written as U S V transpose into X equals to B. From here I can write X equals to U S V transpose inverse into B. This can be written as V transpose inverse, let us say S inverse I am writing as S plus into U inverse into B. So, from here I can write x equals to Since V is an orthogonal matrix, so V transpose is also orthogonal, and here V transpose inverse will become V transpose transpose, which will be your matrix V. S plus and U inverse will become U transpose, because U is also an orthogonal matrix into B. Now, you can easily write V and U transpose, because this you are having already in singular value decomposition of A. Now, the question arises how to calculate this S plus. So, the matrix S plus is defined as so if sigma ij are the entries of S, then the entries of S plus I am defining as sigma ij plus, and this equals to 0 if sigma ij equals to 0, and it is equals to 1 upon sigma ij if sigma ij is non-zero. So, for example, if you are having a matrix S which is m by n, and the rank of the matrix A is R, R is less than minimum of m and n. So, it will be less than m in case of underdetermined system, and less than n in case of overdetermined system. So, in both the case A transpose A as well as A into A transpose will be singular matrices, and hence the inverse of these two matrices do not exist. So, in this case my S will be something of this shape: sigma 1 0 0 0, sigma 2 0, and then I will be having 0 0 sigma r 0 0 0 0. So, these will be matrix A in case of overdetermined system A m by n matrix, and then what I am having so it is m by n matrix. So, these will be total m minus r 0 rows. In this case your S plus will become a n by m matrix now, which is having 1 upon sigma 1, because sigma 1 is non-zero here. So, it will become 1 upon sigma 1 0 0 0 0 1 upon sigma 2 0. In the same way it will become 1 upon sigma r, and then what I will be having? I will be having n minus m 0 rows, because there will be 1 upon 0. So, 1 upon 0 I will replace by 0. We will see this in an example, and then so this will become n by m matrix, which is having now m minus r 0 columns. If you see here, S into S plus will become an identity matrix of R by R and then 0 blocks accordingly. So, in the first R rows there will be 1 in the as the diagonal entries, and rest of the places it will be 0. So, hence in this way we can define the pseudo inverse of S as S plus, and the pseudo inverse of A will become A plus, which is V S plus into U t. So, let us take an example of this. Consider an example of fitting a line through data points, let us say 1 2, 2 3 and 3 5. So, let us solve this example using the approach which I told you just now. So, here let the equation of line becomes y equals to mx plus c. So, here I am having x1 y1, x2 y2, x3 y3. So, now from the first equation I will get, or in matrix form I can write it x1 1, x2 1, x3 1 with multiplied with mc equals to y1 y2 y3. So, please note that in each case the coefficient of c will be 1, because here c is having coefficient as 1. So, if this is my matrix A, this is x, this equals to b, then my matrix A will become here 1 1, 2 1 and 3 1. x1 is 1, x2 is 2, x3 is 3, and here b will become, that is the right hand side vector, y1, y2 and y3. So, now I need to find out the values of m and c. So, it is an overdetermined system. If I perform the SVD of A, then the matrix A can be written as USVD, USV transpose. So, where the matrix U will be a 3 by 3 matrix, because M is 3 here, it is 3 by 2. So, M by N, and the entries of this will be minus 0.3231, 0.8538, 0.4082, minus 0.5475, 0.1832 and minus 0.8165 will be the second row, and third row will be minus 0.7719, minus 0.4873 and 0.4082. Here the matrix S will become a 3 by 2 matrix, which will be having 4.0791 as the first singular value of A, the biggest one, 0, then 0, sigma 2 will be 0.6005 and then a 0 row, m minus n number of 0 row. So, this will be 3 minus 2 1, 1 0 row, and finally V will be a 2 by 2 matrix. The entries of V will be minus 0.9153, minus 0.4027 minus 0.4027 and 0.9153. Here U and V are orthogonal matrices, and we have learned in the previous lecture that how to calculate these matrices. The alternate way of doing it is using the MATLAB software, and there you are having direct command for finding the singular value decomposition as SVD of A. So, if you will perform U SV equals to SVD of A in MATLAB, you will get these three matrices. So, this is just an alternate for doing it to save the calculation efforts. So, I am having now these three matrices. So, now my pseudo inverse of A will become A plus, which will be V S plus U T. Here V will be this matrix, S plus will be now a 2 by 3 matrix. So, it will be 1 upon 4.0791 0 0 0 1 upon 0.6005 0 into U transpose. And if I calculate this matrix A plus, so it will be a now 2 by 3 matrix, because A is 3 by 2 matrix, which is given as minus 0.5 0 0.5 1.3333 0.3333 and minus 0.6666. So, this is my A plus. So, now if I calculate my x, which will become A plus into B. So, A plus into my matrix B is 2 3 5, the vector B. So, which comes out to be 1.5 and 0.3333 as the least square approximation of this system. So, in this way we can calculate the least square approximation solution using the singular value decomposition. In particular, we have used the singular value decomposition for calculating the pseudo inverse. Now, let us make the analysis of it. How we have done it? LSA with SVD, or this LSA I can also write LLS, means linear least square solution. So, for doing this, again consider Ax equals to B, where A is m by n matrix with rank of A equals to R, which is less than minimum of m n. Then if it is an overdetermined system, the least square solution is to minimize square of x minus b, square norm of this, and we have to find out such x. So, if in particular I check about this particular thing, then this I can write as U transpose A V V transpose x minus b. Here you know that V into V transpose is I. So, A V V transpose x will become simply A into x minus b. So, this bracket term is similar to this one. Moreover, I am pre-multiplying this particular vector by U transpose, and in singular value decomposition of A, you know that U and V are the orthogonal matrices. Since U is an orthogonal transformation, so U transpose is also an orthogonal transformation, and we know that if U is orthogonal, then Ux equals to norm of Ux equals to norm of X, means norm preserved under the orthogonal matrix multiplication. So, the same thing I am doing here. Now, this thing I can write ut A V into Vtx minus U transpose into B. Now, A equals to U S Vt. So, from here I can write S equals to U transpose A into V. So, this I am replacing with S. So, S Vt x minus ut b square. So, this equals to this one. Let V transpose x equals to z, another vector. So, from here what I can write, this can be written as S into z minus ut b, this one, or if I open this norm, this can be written as I equals to 1 to r sigma I z I minus uit b, where ui are the rows of matrix U square, and why I am taking up to r, because the matrix A is having only r non-zero singular values. After that all sigma I where I is greater than r will become 0. So, this term will become 0. So, if this will become 0, then I equals to r plus 1 to m, this will become simply this. So, from here I can write z I equals to u I transpose b upon sigma I for I equals to 1 to up to r from the first term, and then it will be some arbitrary for I equals to r plus 1 up to n. As a result, if z I equals to this for first r, then first term will become 0. So, minimum x and the least square error in this solution will become summation I equals to r plus 1 to m uit b whole square. Also, you know that recall z equals to Vtx. So, from here I can write x equals to V into z, because V is an orthogonal matrix. Moreover, the length of the vector x equals to V into V transpose into x, because V into V transpose is an identity matrix. This will become Vtx is z. So, V into z, and since V is an orthogonal operator, so it will preserve the norm, this equals to z. So, from here I can write hence least square approximation of Ax equals to b given as x star, that is the solution, I equals to 1 to R ui t b upon sigma I, this is my z I, and then into V I, because z equals to V transpose x. So, in terms of singular values, I can write the solution of least square solution in this way. So, if we see the earlier example which we have taken for fitting a line, there x star, that is the least square solution, can be given as I equals to 1 to 2, because we are having only two singular values ui t b upon sigma I V I. So, this will become u 1 transpose into b upon sigma 1 into V 1 plus u 2 transpose b upon sigma 2 into V 2. And if I calculate this particular term, it is a scalar value, this comes out to be 1.5072, and then V 1 is now the first column minus 0.9153, and this will become 4027 minus 0.298, this is this particular scalar value, that is minus of 0.298 multiplied by with second column of the V, that is minus 0.4027 and then 0.9153. So, if I do it, it comes out to be 1.4995 and then 0.33342, which is the same 1.5 and 0.333, which we obtained earlier with a plus equals to means which we obtained already with x equals to a plus into b. Hence, the claim is verified. So, this is the another way of doing the analysis of least square approximation using the singular value decomposition, and here we have seen that both the answers are equal. Now, take one more thing, means one more example where we are having 0 determinant. So, take one more example where we are having 0 determinant of the matrix A. So, example 2, solve x 1 minus 2 x 2 plus x 3 equals to 3, 2 x 1 minus 4 x 2 equals to 0, and then x 1 minus 2 x 2 plus 3 x 3 equals to 9, and solve means find out the minimum node solution, means least square approximation of this system. Here if you see, the matrix A is given as 1 minus 2 1, 2 minus 4 0, 1 minus 2 3, and the right hand side vector B is 3 0 9. If you check here, determinant of A comes out to be 0, and hence you cannot obtain A inverse, and you cannot find the exact solution like x equals to A inverse B. So, here if I perform the singular value decomposition of A, then A will become U S V transpose, where U is again will be a 3 by 3 matrix. So, it will, I am writing it So, this is my matrix U. The matrix S will be a diagonal matrix, a 3 by 3 diagonal matrix having singular values of A. So, first singular value is 0, 0, 0, second singular value is 2.5659, 0 and then 0, 0, third singular value is 0 because determinant is 0. So, at least one of the singular value will be 0, and finally, matrix V is given as 4178 minus 0.1596, 0.8944, 0.8355, 0.3192, 0.4472, and then minus 0.3568, 0.9342, and this anti 0. So, here pseudo inverse of A plus will become V S plus U transpose. So, you can write V from here. S plus will become 1 upon 5.780700, 0 1 upon 2.5659, 0 0 0, and according to rule it should be 1 upon 0, but 1 upon 0 is not defined. So, as I told you, for writing the S plus, 1 upon 0 will be replaced by 0 into UT, and this matrix will be a 3 by 3 matrix, and then the solution is given as x equals to A plus B, which comes out to be 0 0 3. So, this is the minimum norm solution, that is the least square approximation of this system using this approach. If we go with another approach, then the solution x star is given by I equals to 1 to 2, because we are having only 2 non-zero singular values, U I transpose B upon sigma I into V I. So, this becomes minus 1 point. So, this will be V 1, sorry, not V 1, U 1 transpose B upon sigma 1 into V 1 plus U 2 transpose B upon sigma 2 into V 2, and if I calculate this particular term, this will be a scalar multiplied with first column of V, this will be again a scalar multiplied with second column of V, this again comes out to be 0 0 3, which is same as x equals to A plus B using the earlier method. So, in this way I have told you the two different way of solving linear systems, in particular finding the least square solution of the linear systems in case when the matrix A is having rank R and the size of A is m by n, and R is less than minimum of m and n. So, in the next lecture we will learn another type of systems, those are called ill conditioned systems, and then we will learn how to solve those systems using the concept of singular values. Thank you very much.